All right, let's dive into one of the most fundamental ideas in all of physics, electric potential. Now, I know that sounds kind of technical, but stick with me here. We're going to imagine a hidden landscape, a whole world of invisible hills and valleys that control absolutely everything about electricity.
You've definitely seen one of these before, right? The classic Van de Graaff generator. It's that magic ball that makes your hair stand on end. And it does that by building up a crazy high voltage. We're talking over 100,000 volts. The effect is super dramatic and visible, but the force making it all happen? Completely invisible. So, what is really going on? How do we even begin to understand this powerful, invisible world? Well, the answer lies in this amazing idea called electric potential.
Okay, so to get a handle on this, let's use a really cool analogy. I want you to imagine the space all around any electric charge as a kind of landscape with its own hills, valleys, and slopes.
The best way to think about it is to connect it to something we already get: gravity. You know how if you put a ball at the top of a hill, it has high potential energy? And what does it do? It naturally rolls downhill. Well, the electric landscape works pretty much the exact same way. High voltage is just like high altitude. A positive charge placed there has high potential energy, and it's going to want to fall toward a lower voltage. It's just rolling down the electrical hill. So, how do we start building this landscape? Well, we start with the simplest thing imaginable: a single, tiny point charge. This little guy is the basic building block for, well, pretty much everything.
Now, the textbook definition says electric potential is the work needed to move a charge to a certain spot. But honestly, the best way to think about it is just electrical height. That's it. A positive charge creates a hill of high potential, and a negative charge creates a valley of low potential. Simple as that.
And this whole landscape follows a really simple rule. The formula here, V equals KQ over R, just tells us that the height, V, depends on two things: how big the charge is, Q, and how far away you are from it, R. Basically, the farther you get from the center of the hill, the less steep it gets. Makes sense, right? Okay, so one charge, that's easy enough to picture. But what happens when you have a whole bunch of charges scattered around, all making their own little hills and valleys? Does the math suddenly get super complicated?
Yeah, look at this. How in the world do we figure out the total electrical height at that one point P when you've got all these different charges pushing and pulling from different distances? This looks like it's going to be a real headache.
Now, if you've ever had to deal with electric fields, you know they're a pain. They have a size and a direction. They're vectors, and adding a bunch of vectors is just complicated. So, do we have to do all that nasty math here? And the answer is a huge, wonderful, resounding no. This is the absolute magic of electric potential. Because potential is just a number. It's a height, not a direction. All you have to do is find the height from each charge, and then you just add the numbers together. That's it. Simple addition. It's an idea called the superposition principle, and it is incredibly powerful. And that right there is the key takeaway, the game changer. Electric fields are vectors. They have direction. The math is tough. But electric potentials, they're scalars. They're just numbers, and adding numbers is easy. This is exactly why physicists love using potential. It just makes life so much simpler. So now that we have this powerful tool, let's apply it to one of the most common and important setups in all of nature: the electric dipole. So what's a dipole? It's just a little team of two, one positive charge and one negative charge, of the exact same strength, stuck a certain distance apart. And when you put those two together, you get this really fascinating landscape. It's a steep hill right next to a deep valley. This specific shape shows up everywhere and is responsible for all sorts of things in chemistry and biology. And get this, it's not some abstract idea. You use this every single day. A water molecule, because of its shape, acts like a tiny little electric dipole. It has a slightly positive side and a slightly negative side. So when you put food in a microwave, the oven creates an electric field that flips back and forth, making all those little water dipoles spin like crazy. That spinning creates friction, and that friction is what heats up your food. It's the electric landscape at work in your kitchen. Okay, so we've gone from a single point to a couple of points. But what about real objects? Like a charged piece of wire or a metal sphere that has charge spread all over it. How do we handle something like this charged wire? It's not just 2 or 3 charges.
It's made of trillions upon trillions of them, all lined up. How could we possibly add all of those up?
Well, the strategy here is actually kind of brilliant. We just pretend the wire is made up of an infinite line of tiny little point charges. We basically chop up a really complex problem into tiny, simple pieces that we already know how to deal with.
And what do we do with all those tiny pieces? You guessed it, the exact same thing we did before. We find the tiny potential from each tiny little charge, and then we just add them all up. It's the same principle of superposition, just on a much bigger scale. So let's pull back and look at the big picture. We've gone from a single electron all the way up to a complex charged object. So why does this idea of electric potential matter so much? At the end of the day, it all comes down to this. Electric potential gives us a map of that invisible world. It takes ridiculously hard vector problems and turns them into simple addition. It lets us analyze everything from the tiniest particles to massive objects. It's not just a math trick. It's a fundamental language for describing how the universe works. And hey, don't just take my word for it. The source material says it perfectly. The real power of potential is its simplicity. By swapping out the complexity of vectors for the ease of scalars, we just unlock a much, much better way to understand physics. We've seen how to map this landscape for points, for dipoles, and for wires. So let me leave you with one last kind of mind-blowing thought. Every single time a neuron fires in your brain, it's creating a tiny fluctuating electric potential. So what complex, beautiful, and dynamic electric landscape would we see if we could actually map the shape of a single thought?